for today's presentation. Similar to other sessions, we will have a 40-minute presentation followed by 10 to 15 minutes Q&A, depending on the time. And as I said, audience can use the chat box to ask their questions, or they can raise their hand, and we will give them the permission to turn on their mic during the Q&A time. For today's seminar, we have Alex Milovanoff, and he is finishing his PhD and starting his postdoc fellowship at the Department of Civil and Mineral Engineering at UT-ITE. His research aims to support the development of sustainable energy systems. We're pleased to have you with us, Alex. We're looking forward to your presentation.
Thank you. Thank you, Mustafa. So thank you all for attending and being here. Okay, yeah, so I'm going to start. Today, I just need to click on that, okay. So today I'm going to talk about climate change, transportation, which is your core expertise in the group, electric vehicles, but other technologies, more importantly, biking and cycling too. And even before I dive into the details of my presentation, I want to spoil the key message here is that if you bike or walk, that's probably the best thing you can do for climate change compared to buying electric vehicles. But now let's a little bit. Let's talk about context a little bit more, and I want to sort of provide you probably numbers that you have in mind or numbers you don't, but I think critical numbers that we need to remember, especially in transportation, but overall in the climate change discussion. So in 2018, there were about 33.5 gigaton of CO2 emitted globally, so in the planet. And CO2 is a greenhouse gas, and so it has effect on global warming. Yes. More importantly, this trend for the last 10 years was about 0.5 gigaton of CO2 per year. So for the past 10 years, there's been an increasing trend, and every year we're adding more or less 0.5 gigaton. So why am I giving you these absolute numbers? It's because there is a consensus that global warming, or the global mean temperature change, is more or less proportional to a global budget of greenhouse gas emissions. CO2 emissions, carbon dioxide, is the major greenhouse gas currently. So a lot of scientists are trying to account for a carbon budget, so a CO2 budget in the next couple of decades. We know that there is sort of an international consensus to limit the global warming at 2 degrees by the end of the century, above pre-industrial levels. This value is more like a political value rather than anything else. I mean, if we reach 1.9 compared to 2.1, there's no real big difference. But there is a lot of uncertainty in terms of what is a tipping point and what value should we aim for. And more scientists and climate scientists are saying that we should probably aim for 1.5. So the larger the reductions are, the better it is anyway. But if we take those absolute values, a study in Nature quantified that we have in the next 30 years between 2000 and 2050, we have between 1,000 and 1,440. So I'll say 1,000 and 1,400 and 500 gigaton of CO2 equivalent. Gigaton of CO2 to be emitted if we want to stay below this 2-degree target. The percentages that I gave, the 75% and 50%, are just sort of uncertainty ranges. So if we want to be below this 2-degree target at 70% chance, we should stay below those 1,000 gigaton. So what does that mean concretely? So now, I give you these absolute numbers. If you're trying to estimate, it means that at the current pace of emissions, we'll probably exceed the budget in 2030 if we want to have a 75% probability of staying below 2 degrees, or 2040 if you want to have a 50% chance of staying below 2 degrees. So I think a lot of people don't realize that the real urgency of climate change is that we only have about a decade do meaningful changes to our emissions. And you'll see that it's really important in sort of the next couple of, it's one of the core assumptions or important point of my study. So in Canada, where are we? 0.5, 0.6 gigaton of CO2, so it's not huge compared to the global average. And Canada is, even though a big country, it has a very, very limited population. But per capita, it's 15.2 and ton of CO2. And the world average is at 4.4. So we are around, I mean, a little bit less than 4 times the world average in terms of ton of CO2, in terms of CO2 per capita. So same issue in Canada. We need to do things because we are driving the emissions up, and the emissions have been going up in the past decade too. 0.57, the value we had in 2018-19, is the highest value we never had. We've had. So global key point: there's an urgency to act. But now I wanted to dive a little bit more into the GHG emissions in Canada, and you're probably aware of this. But the point here on the left, you can see a graph where you see the Canadian GHG emissions divided by different sector. Transportation, 25%. But an important point is that these emissions only account for the combustion during the process. So combustion associated with transportation. Oil and gas in Canada also account for 25%. But these oil and gas are responsible for 25% are being used in other sectors, especially transportation. So there's first this understanding that transportation is more than 25% because we need a lot of resources in order to transport our goods and passengers that have emissions upstream. I'm going to come back to that. If we dive into transportation, passenger cars and light trucks are about half, a little bit less than half, and freight is a little bit less than a half too. So key message here: transportation is the main driver of Canada emissions, and that's one of the highest ratio in the world. And passenger transport is the main driver of transportation emissions in Canada. So I hope you had that in mind, but I think it's always important to put back values in what we're trying to solve. So GHG emission mitigation in transportation. I think there is a huge hype right now, and a great one, on electric vehicles. I don't know if you saw the news a couple of weeks ago. A team in Windsor won sort of a prize to design the first all-Canadian electric vehicle to be virtually engineered. It's an exciting topic. It basically means that we're trying to build in Canada the capacity to design the vehicles. Do we have the capacity to build them? That's not yet, but the federal government, the provincial government in Ontario decided to invest $500 million to produce vehicles in Ontario to manufacture the batteries, and that's the first investment of this sort in Canada. So that I think we are living a time where electric vehicles are definitely getting the spotlight, and Canada is moving forward. Canada has a target to have 100% of sales being what they call zero emission vehicles by 2040. So this is definitely a big time for EVs. For example, a couple of weeks ago, for many reasons, but Tesla was the most valuable car company in the planet. And so, a lot of signs are showing that EVs are definitely going to change our transportation systems. But there is, very few discussions around are there enough or not. It seems to me that when we talk about EVs most of the time, there's sort of no real threshold on how much we need them or whatever. It's really saying they're going to come up and they're going to solve all our problems. One of the key aspects we need to look at EVs and any alternative technology is by saying they have different implications in terms of greenhouse gases. So life cycle assessment is a very common methodology used to assess different and alternative technologies and products. What we do with life cycle assessment is we evaluate a product across the life cycle. When we apply life cycle assessment to passenger transport, we look at the vehicle cycle. So what do we need to produce the vehicles, the resources that are being extracted, the material component productions, the vehicle manufacturing as well, the operations. So combustion of the fuel when when the vehicle uses fuels such as gasoline or diesel, and the end of life too. So those different stages have emissions. There is the fuel cycle as well. So in order to feed these vehicles, we need some fuel. We need to extract them, to manufacture them, distribute them, etc. As I said before, gasoline, diesel, they have huge extraction emissions. But electricity is a very interesting one because electricity does not have any operation emissions, but have a lot of production emissions. Obviously, electricity doesn't come from, it's not naturally found, so it's something we have to produce. And also another aspect is infrastructures. What are the infrastructures that we need to develop? The charging stations, the electric chargers, the roads, etc., for a given transportation mode. So life cycle assessment needs to be used when we're trying to assess this overall picture. If I go back to electrification, I think I mentioned that, but yeah, the GHG emission implications is that the batteries are more energy intensive. And so they currently have higher emissions than normal conventional components. That requires materials, critical materials that are being extracted with also high energy use in inputs. They require electricity. In Canada, about 20% of the electricity comes from fossil fuels. So this is not a big number. In the US, it's about 60%. But if you go in Alberta in Canada, it's about 90%. If you go in British Columbia, or in Quebec, it's almost zero carbon electricity. So there is a huge variability that we need to take into account and see what are the changes, etc. But at the end, no exhaust emissions. So that's why they're being called zero emission vehicles. I personally don't like this term. I think it's a misleading term, but they can help at reducing the emissions. I'm going to see a little bit why. But one of the key aspects is that climate change, we need to act urgently for climate change. We have a budget that is dwindling. But any solution we're trying to implement will take time to be implemented. And that's one very important aspect is the dynamics of the mitigation measures takes time, and we need to assess them taking into account this climate change windows and climate change frame. And for example, if you want to transition from conventional to EVs, let's imagine that next year, every single new vehicle that are being sold are EVs, and it will still take 10, 15 years to completely renew the fleet and to only have EVs on the road, probably 15 to 20 years, unless strong measures and we prevent people from using their conventional vehicles, etc., which has huge equity problems. So the problem is, and that's the same for any other solutions, because it takes time, we need to assess them, taking a realistic picture of what could be done or not. So one of the projects that I led, and the one that I sort of want to present you today, is we actually took that into account to ask a very simple question. How many on-road electric vehicles are needed to remain within the US passenger car fleet GHG emission budget? So if we're able to look at a budget for the US passenger and private car fleet, and if we're able to realistically model what will be the transition of different alternative technologies in the next decades, and then maybe we can answer this question: how many enrolled electric vehicles do we need? So to answer this question, we developed a model that I call the Fleet Lifecycle Assessment and Material Flow Estimation model, the FLAME model. And it has basically one objective. It assesses the current and prospective GHG emissions of a given fleet. So what does it do exactly? First, it defines different technologies. So we have 4 modules. I'm going to talk about the first one, the vehicle module. And what we do is we characterize the different vehicles. So how much fuel is being used by a conventional vehicle? How much fuel is being used by a conventional electric vehicle? We actually look at hybrid electric vehicles as well, plug-in hybrid. We actually look at different sizes. If we look at cars and light trucks, because the light trucks are heavier, and they have higher energy intensity. And so we actually dived into the details of these technologies. We looked at their weight, we looked at their components and how the components can affect the weight, can affect the fuel consumption. We look at how the engine efficiency can affect the fuel consumption and the weight, etc., etc. So that was the first part of it, was characterizing all those different technologies that are representative of the private passenger fleet. The second module is about quantifying this fleet turnover, trying to quantify how many new vehicles will be sold, how many old ones will be outgoing, will be scrapped, and how many takes it will take, how many times it will take, how much time it will take to renew an entire fleet. When we combine those different fleet turnover modeling perspectives with the vehicle modules, you can start of calculating the energy use, taking into account the improvements in fuel consumption for new vehicles and etc. And then we also developed what we call an automotive material flow module. So we actually calculated the quantity of primary and secondary materials that were going into these EVs and the quantity of scrap material that were going out. And more specifically, we look at the batteries materials such as manganese, cobalt, and lithium, trying to quantify the material flow implications of deploying alternative vehicles. And at the end, we apply those life cycle assessment tools to quantify the GHG emissions, taking into account the vehicle production, the fuel use, the vehicle end of life, material extraction, etc. In order to build all of this, once we have this flame model, we need to estimate a budget that is consistent with a certain climate target. And as I said before, we have a global budget, but now we need to downscale this budget to a given sector for a given country. There's many methods to do that, and I think there's many different controversies associated with those methods, because obviously a budget for a given sector and country will depend on the budget for the other ones. But we use actually something called the integrated assessment models, that are huge models that simulate realistic pathways for many different countries and sectors, trying to build budgets that are sort of realistically consistent with what could happen. That was one of the methods. We basically quantified this budget for the US private passenger fleet. And then we developed an optimization procedures to quantify the level of EV deployment that we need to remain within the budget. So we played with the flame model, we played with the quantity of new EVs that are getting out, we played with many parameters, and with the integrated assessment models to try to quantify and answer this big question of how many EVs do we need in the fleet. So to give you some practical values before we dive into, I give you some practical answers at this question. Currently in the US, an electric vehicle, so on average in the US, will reduce the GHG emissions per kilometer traveled by 65%. So you can see on this graph, here you have 6 different vehicles that are being compared. The 3 top ones are light trucks, conventional vehicles, so ICE EVs, internal combustion engine vehicles, and 2 different types of battery electric vehicles. We have the long-range battery electric vehicles, such as a Tesla model. I'll say 3 long range, or any other Tesla. Actually, they have all long. They all have long range batteries, so it means that we can drive long distances. And the short ranges, the BV100, are, for example, the Nissan Leaf or other smaller vehicles. And cars are smaller vehicles. And so we can see that BEVs in the US reduce the emissions. They have higher vehicle production implications in battery, especially implications. They have no fuel use, so that's the blue part of the bar, but the fuel production is higher too. But in the US, based on 60% carbonized electricity, the reductions are still getting down. So when we ask these questions, that's sort of the first thing we quantify. We basically quantify the current policies, pathways, how much are they consistent with the budget we quantify in the US? So I need to talk about the 3 different panels you can see here. There are 3 different scenarios. Basically, nobody knows what will happen in the next decades. So you had to build scenarios in terms of big socioeconomic components. We use the framework called the shared socioeconomic pathways, SSPs, that sort of develop assumptions regarding economic development, population, etc. And we use this framework to quantify this budget. And so that's why we always have 3 different scenarios that represent 3 different potential futures. SSP1 represents a very sustainable future where we assume that population will not increase that much, economic development will go along with development of renewable sources, and people will be more aware, etc. SSP5 is the opposite. It says that we have a heavy fossil fuel development, economic development is huge, but driven by fossil fuels and population is getting up, etc., etc. So those are critical components we assessed within our study. And so what we can see with this graph is that basically the current pathways are definitely not enough to be consistent with our climate ambitions, 2 degrees according to the Paris Agreement, even though the US is not in the Paris Agreement, but hopefully we'll be back soon. So here you can see the blue lines are the baseline, assuming no changes to the fleet. The first brown part is the growing fleet, because most people agree that there's going to be an increase in travel demand in the US in the next decades. And we're going to come back to that a little bit later on. The decrease in what we call the safe standards are fuel economy standards, so improvements to the current conventional technologies. And then we have 2 scenarios calculating the reductions associated with an optimistic pathways for electrification. There is a scenario called the EV30 at 30 developed by the International Energy Agency, which basically is right now one of the most optimistic projections. And even if the US implements those, we still have mitigation gaps. So from this, we ask the question, how many electric vehicles do we need in the US if we want to be consistent with this 2 degrees climate target? And so that's these 2 graphs present the result of this question. On the left, you have the fleet stock in terms of million of units that needs to be deployed in the US. And on the right, you have the resulting share in the fleet. So what we can see on the left is basically we need a minimum of 270 million EVs by 2050, up to 350 million EVs by 2050. And that represents about 90% of the vehicles in 2050. And so that's actually quite consistent across the 3 different scenarios, SSP 1, 2, and 5, that represent very different socioeconomic interactions. But because there's many nonlinear effects, at the end, we have quite consistent results. Well, so now if we compare that with the current business as usual, in the US, the US Energy Information Administration developed their reference scenarios, and in their business as usual scenarios, they assume that only about 12% of the fleet will be electric in 2050. The most optimistic projections that we can build from the International Energy Agency that assume a 30% global EV in new sales by 2030, and then an increasing. At the end, only result in about 50% of EVs in 2050. And the reason is because it takes time for these vehicles to be and to make meaningful changes. Basically, if you want to get 90% of EVs by 2050, you only need to have new electric vehicles sold starting 2035. And that's what the California ban is planning to do. But now, can you realistically imagine California ban applying to the US entirely? Maybe. And so, at the end, I don't have the answer of is it feasible or not, but we looked at all the components associated with this massive electrification. One component is, first, you need to remove important EV adoption barriers. The huge current EV adoption barriers are sort of more awareness for the drivers. So, for example, the range anxiety. Most people believe that with an EV, they will not be able to do everything they are currently doing with the vehicles. That's not entirely wrong, but for the vast majority of the trips, this is actually not accurate. People will be able to drive currently with an EV for the vast majority of the trip they're doing. We need to make sure that people are aware of these different aspects. Obviously, right now, one of the biggest adoption barriers is that the EVs are way more expensive. The cheaper Tesla is still twice more expensive than the average price for a conventional vehicle in Canada. So with the higher purchase cost, obviously we cannot expect people to move massively to EVs. So we need tax exemptions from the government, for example, subsidies or huge taxes for the conventional vehicles, even though there's a lot of equitable problems associated with that. But that's a big adoption barrier. And the last one, an important one too, is we don't have the infrastructures. In my house right now, I live in Toronto, on the east of Toronto. I don't have an electric charger around me or even nearby. Maybe you do have one in your condo, but many condos don't have to. So if we want to make sure that in the next 10 years or 15 years, we have only new electric vehicles, we need to answer those questions and many more. And one of the things we looked at are the potential strains on the electricity infrastructures, because EVs rely on electricity. In the US, if we electrify 90% of the fleet by 2050, we add about 40% of additional electricity in 2050 in the US. So national electricity demand could go up by 40% in 2050 if we electrify massively. The thing is that we need this electricity to come from clean sources, solar panels, hydroelectric power plants, wind turbines, etc. And the fact is there is also a difficult discussion here between how do we coordinate a larger share of renewable sources and in the fleet, in the electricity infrastructures, knowing that they have different attributes and different capacity factors. And potentially a 40% in electricity demand for EVs requires an even larger electricity capacity installed from renewable sources, because they are not that responsive and they're not always reliable. So we need to also look at what would be the impact on the electricity infrastructures. And once again, it's feasible, but the higher the electricity demand will be in terms of decarbonizing the electricity, the more difficult it will become to decarbonize the electricity. And finally, we looked at the strains on the critical material supply chains. We looked at cobalt, manganese, lithium more exactly, and we realized that, for example, the lithium needs, in order to get this 90% electrification by 2050, even assuming the current technology pathways and improvements in batteries following what the International Energy Agency of many other institutions are saying, we could potentially require just in the US about 30%, 1/3 of the global lithium resources only to electrify the US. So now if you start thinking that Canada needs to do the same, Europe needs to do the same, China needs to do the same, India, etc., then the lithium resources are not probably enough currently. So there is a lot of discussions among researchers. There's many uncertainties associated with that. We are discovering new lithium resources all the time. So it's not an absolute answer, and technologies will probably get even better than what we assume in our study, and new technologies will be deployed too, solid state technologies with different types of critical materials. So once again, it's not an accurate answer, but potentially we're going toward a future where we have supply chains for critical materials that are not that are highly tensed. Knowing that lithium, for example, is mostly located in few countries, Chile, Australia, cobalt is mostly located in Congo, and manganese in other countries, we can imagine a place where we stop relying that much on fossil fuels and started relying on other types of critical materials. And that's probably not something we want to go forward to that much to. So I think here the point is we have some absolute numbers problems. But maybe I wanted to do this little sort of a game with you for the few people that are listening. But maybe the question that we can ask, and if we look at these different factors, what do you think are the most influential parameters that? What are the most influential parameters on the answer that I provided? So I don't know if we can do that, and I don't know if people are listening right now, but if you can, answer in the chat, what do you think is the most influential parameters to the number of EVs we need to deploy by 2050 in order to be consistent with the climate target? So I hope you understand the question, and maybe in the chat if you can just answer, I think it's a number 1, number 2, number 3, number 4. So the number 1 is the fuel economy standards for the conventional vehicles. So the fact that the conventional vehicles right now needs to reduce we need to ensure that the standards for their fuel economy and fuel consumptions are quite important, and so reduce their energy use. The weight of the EVs, do you think that the weight of the EV matters? If, for example, the weight of the EVs are going up, and if we deploy only light trucks for electric vehicles, do you think that actually makes a big difference in terms of the results we're getting. You think that the sources of electricity is a huge parameter, meaning that if the electricity comes only from renewable sources, then no, we actually need way less vehicles. And finally, do you think that the vehicle ownership and usage rate is the critical one? So I don't know if people can start answering. So I can see four must, then 3, 2, 1, 4. Yeah, that's indeed your Sina. Thank you. 3. So I'm gonna give you 10 more seconds. Okay. So what we simulated in our model, indeed, we looked at these different factors and trying to build scenarios realistically and trying to look at how different factors could influence the overall results. So in the graph on the left, you can see the resulting share in the on-road stock, depending on how we change the different factors that are consistent with the climate target as I described before. So there are 3 bars for each panel just because there are 3 different scenarios, but you can see that they're quite consistent. And so the first parameter, the vehicle weight control, doesn't really matter that much. The reason is because EVs are more energy efficient than conventional vehicles. So a light trucks use way more energy than a conventional car and has way more emission than a conventional car. But a large EV does not have the same absolute increase in emissions or in energy compared to a conventional EV or small EV because they are more energy efficient. We can start talking about how a larger EV requires even more materials and create more constraints to some of the tensions we've looked at. But from a pure GHG emission perspective, that is not a critical factor. Fuel economy standards are quite critical in the short term because if we're able to increase the efficiency of the conventional vehicles rapidly, starting next year in a couple of years, it's going to make a big difference on the long term. And that doesn't really require, it's not something that can take years and years because manufacturers have developed their technologies and they can implement some more efficient ones. That's an interesting, important parameter, but that's not a critical one. The electricity sources is an important parameter. So in this panel, electricity emission factors, we actually simulated a case where we assume that the electricity is 100% clean. And that's sort of the far left case. And on the far right, we assume that we don't change the electricity source in the US. So we assume that in the next 30 years, we're going to have 60% of electricity based on carbon. And what you can see is that even if the electricity is completely clean, there is still a huge amount of EVs we need to deploy. And the reason is quite simple. It's because if you don't deploy an EV, and if you don't change the transportation system, then the conventional vehicles are still here. So the reduction potential of EVs are mostly depending on 2 factors. First, it's their vehicle deployment, and second, the electricity sources for electricity. Meaning that if we really want to reach meaningful reductions and be consistent with our climate target, even if electricity is completely renewable, we will still need at least 50% of the fleets being electric vehicle. I mean, even more than that, 50%, being EV by 2050. Because every time we don't replace a conventional vehicle, it's still a vehicle that is emitting. So obviously, the biggest and most influential factor is the vehicle usage. Because vehicle usage is not only about the vehicle usage in a given time, it's the trend of vehicle usage. And in the US, we've had increasing vehicle ownership and vehicle usage in the last decades. And so if we continue the trends the way we assumed in our default scenarios, then that brings us to a case where we have a lot of private cars on the road or private cars used, and they have high emissions. And the pathway between those two creates more tensions to the system. But if we're able to reverse some of those trends, and that's what we simulated in the left case of this last panel, then we actually can reduce the emissions drastically if we're able to reverse the trends in vehicle usage and ownership. So obviously, I'm not saying it's easy to do, but I'm saying it's important to keep in mind that the most critical factor when we talk about GHG emissions of private cars is really how much we use them. And that's really something we need to keep in mind. And the electricity is an important one, but only when EVs are fully deployed. Okay, so so that's basically the study that we did and that we published in Nature Climate Change. And we did other studies before, and I don't want to spend more time on this, but I want to show you some other things that provide the similar results. For example, ethanol is a biofuel that derives from crop, and it has very different life cycle emissions compared to conventional gasoline. I'm not going to dive into that too much in details, but it extracts emissions during the crop aspect. It has emission production during the farming aspect and the ethanol production, and also have exhaust emissions. Different vehicle life cycle. It's a bio-based emissions most of the time, so very different impacts on greenhouse gas impact. But we simulated the same types of calculation that I did before. We looked in Canada for this particular case, and we looked at how much ethanol can we deploy in Canada and what are the reductions we can get. And if we compare that with the target in 2030, the current target in Canada, which is not, by the way, a consistent target with climate change, with the 2 degrees climate change, but which is quite the best target you can find. And I'm not going to spend much time describing this graph, but the key aspect, the key point is, even if we fully deploy ethanol in Canada, and if we don't change the transportation system, and we keep up, if we keep on having growing fleet stock, we will not be able to reach the target in the transportation sector, or at least even for the private passenger cars, rapidly enough. And because ethanol is not a burden-free fuel and will never be. So I think we need to take a step back, because I don't want you to think, oh, we'll never be able to reach anything. I want you to think that the case studies I showed you before, electric vehicles, ethanol, are only dealing with one part of the problem. Because if we take a step back, and if we look at the mitigation measures in transportation, they're very often characterized in 3 different categories: avoid, shift, and improve. First, emissions and mitigation measures depend on how much we can avoid the need for travel. If we can reduce the frequencies for some of the travels or reduce the trip length, then we will be able to avoid the need for travels and so have reduction emissions. It has to be about land use, obviously. It has to be about the way we work. For example, teleworking is one specific way that can reduce our personal trips and commutes. It has to be about where we live compared to where we work, etc. So I know that some of you a lot of you in transportation group are working with these types of problems. So you know way better than me the actual measures and the difficulty of implementing them. But that's one way. The other way is, if we assume that, okay, people don't really change the way they live and don't really change the way they work and the place they work and, do the same frequencies, we can still shift the mode of transport, from the higher emitting modes to the lower emitting modes, buses, subways. And so this shift will reduce the emissions. The last aspect is improving the technologies, getting higher fuel efficient vehicles, electrifying the vehicles, deploying alternative fuels, etc. Those aspects only improve the fuel carbon intensity or the vehicle carbon intensity. And so that's only if you look at the 3 pictures that you can actually start creating meaningful aspects. And so in our work, we basically realized this, that if you reduce the vehicle usage in the last decades in the US, you can reach the target with the current pace of electrification. What does that mean? It basically means either trying to have intense land use policies, urban land use policies that are oriented toward either transit development or reducing the energy need of transport, or deploying massively public transit in the US in order to reduce vehicle use and ownership. So there's many other ways. It's not easy, and it's really not the core of my research, but we need to keep that in mind, that electrification itself only deals with one aspect and one side of the problem. And so we shouldn't be fooled by the fact that they will solve entirely the problems. We should look at the pictures and always find the solutions that are in the intersection of those 3. And I'm pretty much done. I want to talk about something else, but it's really not important at this point. I wanted to finish with this because I know that a lot of you are working on new mobility solutions. So I'm sure, I wish you have questions on this, but what about new mobility solutions? I actually found a report 2 days ago, which I would be very happy to share, built by the International Transport Forum, which compared life cycle emissions of different modes of transport. I don't want you to go through, obviously, this different list, but I want you to look at the trends for the different types of transport in an urban environment. Public transit are considered as being the lowest emitting in terms of greenhouse gases modes of transport, if you take into account the vehicle component, the fuel, the infrastructures component, and the operational services. Currently, ride sourcing and ride hailing are one of the more GHG emission intensive mode of transport. The reason is mostly because of operational services, deadheading, the fact that very often the travels are empty and without no passengers. Because private vehicles are inherently less energy efficient than buses or bus subways. Obviously, it depends on how much we occupy those buses and subways, etc. Private cars are obviously highly intensive. But what I want to emphasize is, for example, biking. If you take into account the biking infrastructures, biking production, etc., and even for e-bikes, biking are probably the lowest GHG emission intensity modes currently in an urban environment. So there's many things in this picture that are not taken into account. The fact that, yes, ride-hailing can maybe help public transit in some places where people will do some of the ride-hailing transport in order to reach public transit. But also in the other way around, ride-hailing can actually be detrimental to public transit in the sense that more ride-hailing will decrease public transit. And all those different values are point estimates and depend on how much do we produce the electricity, what is the occupancy of those different buses, taxis, ride sourcing, etc. What about car sharing? If you increase the occupancy, obviously you decrease the emissions, and many other factors. But I think those trends, you need to keep them in mind that the new mobility solutions are not, by definition, I would say, climate friendly. And many other things in the discussion that I will be interested in studying that I don't. Infrastructure requirements, what are the GHG emissions, and impact between infrastructures and reductions. Optimal investments too. We need a lot of investments in EVs, but if we also need a lot of investments in public transit, what is the optimal investment? And I wish I would have an answer. And obviously at the end, air quality impacts, because public transit, non-electrified, have higher air quality impact than electric vehicles. But public transit that is electrified will probably be even better than electric vehicles. Okay, so the key takeaways, there is an urgency to act, and it's really something that is emphasized a lot, I think, but we still need to say that. We probably only have about a decade of emissions at our current level, so we need to act, and everything takes time. Technology is only one part of the solution. Technology is by definition what emits the emissions, but there's many upstream events and factors that influence it. And so we shouldn't focus completely on this. We should also look at the big pictures. And a very broad statement that I wish that you have in mind is we need to rethink our transportation systems and the needs that we're having. If we need to look comprehensively at the different mitigation measures and ask the question of what pathway can we should go forward to. Okay, that's pretty much it. I invite you to continue the conversation, see if you have any questions. I wrote an article for the conversation to sort of talk a little bit about my research. Yeah, let's keep in touch. If you have any question right now, I'm also available.
Thank you so much, Alex. So we have time for 1 or 2 questions. So audience, if they want, they can use the chat box to ask their questions, or they can raise their hand, and we'll give them the permission to turn on their mics. Okay, seems we don't have any question. Thank you, Alex. We really appreciate your presence, and yeah, the seminar is finished right now, so if anyone want to leave, we can.
Okay, thank you so much. Have a
Thank
nice
you.
day.
You too. Bye.